We often learn about science as if it were a rigid, completed list of facts. The popular image is a lone genius working through a strict checklist to arrive at an absolute truth, which is then bound in a heavy hardcover and placed on a shelf. That illusion creates a serious problem for public trust. When the morning news announces that researchers have changed their minds about a dietary guideline or a medical treatment, people often assume the scientific process is broken. But active science is messy. It is a creative process fueled by constant failure and revision. To see how real knowledge is actually built, we have to look past the successful results and examine exactly what happens when an experiment goes completely wrong. Consider a simple, everyday hypothesis. Based on the assumption that bacteria cause morning breath, you might predict that human saliva contains its highest concentration of bacteria immediately upon waking up. This simple chart shows the results of an experiment tracking those bacteria levels throughout the day. Instead of a morning peak, the data reveals a massive contradictory spike in bacteria right before going to bed. This outcome isolated a variable nobody expected to find. The experiment succeeded because it identified exactly what was driving the result. Looking at this updated chart, we can see the impact of that variable. The researcher realized that on the night before the anomalous reading, they forgot to use mouthwash. By isolating that omission, the data suddenly makes sense. A wrong hypothesis eliminates an incorrect assumption. It forces researchers to ask a smarter, highly targeted question for the next round of testing. When we scale that concept up to historical breakthroughs, we see the same pattern. In 1928, Scottish microbiologist Alexander Fleming went on vacation and left his lab in a notoriously sloppy state, accidentally ruining an active and delicate bacterial culture. Upon his return, Fleming paid close attention to the contamination. He observed a specific mold growing in the petri dish, actively clearing a ring of space by killing surrounding bacteria. He isolated that mold, known as Penicillium notaeum. Within a decade and a half, his ruined experiment led directly to the mass production of the world's first true antibiotic. In 1895, physicist Wilhelm Röntgen was experimenting with cathode ray tubes and failing to control the rays as he intended when he noticed an unexpected glow on a nearby screen. He investigated the deviation from his expected results, a move that produced an entirely new form of medical imaging. But relying on a single scientist's interpretation of a failure introduces a risk. How do we know they aren't simply twisting data to fit personal biases? The broader scientific community exists to stress test those unexpected claims. A new finding is immediately subjected to aggressive peer review, and other labs attempt to replicate the experiment to see if the anomaly holds up. Scientific ideas survive this filter because the underlying evidence is robust enough to withstand relentless scrutiny from competing experts, not because a particular theory happens to be popular. The scientific method is rarely a straight line leading directly to an absolute truth. It functions as an infinite, living loop of observation, failure, and revision. When you read that nutritionists have reversed their stance on a specific fat, or that astronomers have redefined what constitutes a planet, you are watching that loop in action. Constant shifting is the hallmark of a healthy system. Tentative findings provide evidence that the process is actively integrating new observations and correcting itself, rather than blindly defending outdated beliefs. Science provides a resilient framework for exploring the unknown. In this framework, being dead wrong is often the crucial first step to discovery.